All right. Good afternoon, class. Good morning, good evening, whatever time it is when you're watching this. This is our day 18 lecture video as we're going to continue into chapter 7, talking about how do we actually create confidence intervals. All right. So I'm going to share my screen here as we get started. So going over the schedule, this is our day 18 lecture covering sections 7.2 and 7.3. We're going to talk about how to determine these confidence intervals. We can do this using z-scores. We're also going to have to use something called a t-score for some special case situations. We'll talk about that in 7.3. And this will be building up to getting us towards the end of chapter 7 as we talk about different types of confidence intervals in 7.4 and 7.5. All right. So that's where we're headed here. We do have some other homeworks that are coming up. They're going to be due. So if you have any questions about those homeworks, please, of course, let me know, reach out. I'm happy to help. And, if you do have questions, email me. We can certainly talk about it. And I'm happy to help show some step-by-step directions for any homework questions you may have. Okay. Let's go ahead and get started here in section 7.2 and 7.3. I'm going to turn off my screen share as we're looking at this. And in 7.2, and all right, guys, I should back up and say for 7.1, the whole purpose of these sampling distributions is that we're trying to use a bunch of samples to try to approximate some parameter, oftentimes the population average, which may be unknown. But even if I create a guess for what we think it could be a little off. So we want to create an interval. Well, is it this average, but then plus or minus some number to create an interval for what we think it could be? So what would be a good interval to create? If we back up to the normal distribution, which is the distribution we've been studying here, and I have a guess for what I think the average is. This is the sampling distribution average for what I think the average is, but it might be the true population average might be a little to the left or a little to the right. Okay. But how far to the left or how far to the right should I go? We know using z-scores, if I go some amount to the right, I can look at a z-score here and calculate the percentage for this region. And if I go the same amount to the left, then I have some percentage which is in this region. And then there's some outside region in the tails here, okay? Now, if I want to be confident in this answer, or rather this region that I'm choosing to create, then I want this to include a large window for what the average could be. What would be a large enough window? Well, if this, for example, includes 95% of the data or the population, then okay, that's a pretty good confidence, right? I've got 95% confidence that the true average is somewhere in here, in which case I want 47.5 to the right, 47.5 to the left, and then there's only a 5% chance, or 2.5 to the right side, and 2.5 to the left. There's only a 5% chance that the average is actually farther away. I have my guess for the average, but then within this 95% window, this is 95% of the population. The average should, with 95% confidence, be in there somewhere, right? There's only a 5% chance it would be farther in one of these tails, okay? So in order to create this 95% confidence, I need a z value where this area is 47.5%. Okay, so what z should I use? This z that we're going to use is 1.96. And we're getting that from the normal standard table. Okay, how do we know that? I'll share my screen here as we're looking at the table. So this is in the appendix of the textbook, looking at the normal curves area. So I'll share my screen here. And so what's special about 1.96, here's normal curve area. The shaded region, this is telling us the probability between the middle up to some z value. So if z is 1.96, we see 0.90, 0.91, 0.92, 0.93, 0.94, 0.95, 0.96, and lo and behold, with a z value of 1.96, there is exactly 0.475, or in other words, 47.5% of the population is in that window. So the z-score of 1.96 is the magic z that we want to use if I want a confidence interval with 95% confidence. All right. So what would that look like? Well, the way this is being created is that I have some average. I have a guess for what the average is. And then I'm going to do plus or minus. Well, plus or minus what? I want to go some number of standard deviations to the right and some number of standard deviations to the left. In fact, I want to go 1.96 to the left and right. And so this is 1.96 standard deviations. So I have to multiply by my sample distribution standard deviation. This allows me to create an interval for 95% confidence. So this will give me 95% confidence in my interval that we create here. Okay? So this gives us kind of a starting notion of how to create these intervals. Now, sure, we could move the confidence. Well, what if I want higher confidence? What if I want lower confidence? What about 90% confidence instead? Or 99% confidence? What if I wanted to get that instead? All right. So, but first, let's look at examples where we create these intervals with 95% confidence. This is the formula that we're going to use here. Okay, so go ahead and write that down. And then I'm going to erase what we have here, although I'll keep the formula here. And we're going to look at this example from the textbook. All right. So this is example found in section 7.2. Where we're considering a large hospital, and they're trying to estimate the average length of stay for their patients. But they don't know what the true population average is. What is the true average for how long patients are staying? They have no idea here, right? They're just trying to make a good, educated guess. So they want to, in this experiment, they want to estimate the average number of days a patient stays at the hospital. All right, so this is what they're trying to do. And in this attempt, they collect some sample data to try to make a guess. These are random samples. So they take a random sample of 100 patients. So we know our sample size here, and luckily, okay, 100 is a big number or big-ish. So we should have some hope that this may be an accurate sample of the population. They take a sample of 100 patients and find a sample average of 4.5 days with a standard deviation of 4 days. Okay, so this is the information they have and which has been collected from the sample that they've gathered. So now, with 95% confidence, what is the population average? Right? Because this is only a sample average from the sample of 100 patients. We don't know if this is the true average. So we're going to create an interval. So I will have 4.5 plus or minus 1.96 times the sampling distribution standard deviation, which we've seen this before, is calculated as my standard deviation divided by the square root of the sample size. Okay, so this creates an interval where I do plus or minus. If I do the minus side first, I'm going to have here 4.5 minus 1.96 times 4 divided by the square root of 100, which luckily is 10, so that's not so bad. Put it in the calculator. And we get an answer here of 3.716 for a lower bound, up to an upper bound of, if I add 1.96 instead, then I get 5.284. So what can we say here? Well, with 95% confidence, the true population average is somewhere between 3.7 and 5.2 days. So 3.7 is pretty darn close to 4, right? But 5.2 is greater than 5. So like 4 to 5 days on average, okay? And so they're able to create this estimate, which may be helpful in terms of the planning purposes of the hospital. Maybe they have a shortage of beds which are available for patients. In which case, they need to know, well, approximately or on average, when is the next bed going to become available? Can they then accept more patients, or do they have to wait until they have more space and then they can accept more? This then becomes part of their planning process to understand, like, well, how many patients can they accept if, on average, they're going to have some beds available in the next few days? And that then becomes a maximization problem in terms of maximizing that they want their hospital beds to be full. Ideally, I mean, if they're trying to, if the hospital is trying to make money to stay in business, but if the hospital beds are too empty, well, then they're losing money by keeping the hospital open. So there's kind of this balancing game they're having to play. Okay. So this is a great example of trying to create a 95% confidence interval using this formula here. But in general, what if I want a different confidence level? What if I want 96% confidence, 97% confidence, 99% confidence? How do we do this? This all comes from looking at the Z table for what Z is going to give us that confidence level. All right. So let me rewrite this in a different fashion. Now that we've done this example, and we got the Z value of 1.96 because, well, whatever confidence I'm looking for, then let's see, make sure it's on the board. It is, all right. Where I have this guess for the average, I'm going to go some amount to the left, some amount to the right, where this is the average plus some number of standard deviations. And then the average minus some number of standard deviations. But the trickiness is, okay, well, what Z should I be using here? So I have Z times standard deviation, Z times standard deviation. This Z is determined by the confidence level. If I'm going to have, and I'm going to write it this way, 1 minus alpha percent confidence, where alpha is the probability for error. So look at how this works here. When we had 95% confidence, then alpha was 0.05. In other words, alpha was 5%. There was a 5% chance that the true average was actually somewhere out here far away in one of the tails. So whatever alpha is, ideally we want that chance for error to be small, but half of the alpha is to the right, and half of that alpha is to the left, since the true average could be in the left tail or the right tail, okay? So then whatever my z is, let's call it z alpha over 2, then this z is determined by the alpha. Where, well, okay, if I have 5% is supposed to, or sorry, 2.5% is supposed to be over here. When we had 95% confidence, 2.5 was to the right, 2.5 was to the left. And so this region here is supposed to be 0.5 minus whatever half of that alpha is. When we were looking at 95% confidence, this region here was 47.5%, right? 50% minus 2.5. And so we can find z based off of, well, what z in the z table has a probability which matches that area. All right. So what z matches 0.5 minus alpha over 2, and we can find any z score for any alpha or any confidence level we like. All right. Now, unfortunately, it's not always exact, as the table might have probabilities which are close to what we're looking for. We got lucky with 1.96. That was exactly 0.475. Unfortunately, it doesn't happen with all confidence levels, but the textbook here has done some work for us to make it easier, where they've already done some calculus in the background to figure out some of these z's, and they give us a handy table for this situation. All right, so this sample information for the z's is found on page 320 of the textbook. I'm just going to go ahead and share my screen here as we're talking about this. All right. So how do I read this table? First, we have the confidence level on the left side. How confident am I trying to be? If I have 95% confidence, alpha is 0.05, which means alpha over 2, that's half of the error, is 0.025. The z, which corresponds with that alpha over 2, we already know is 1.96 if we're trying to do 95% confidence. All right. But this handy table tells us what is my z alpha if it's 90%, if it's 98%, or 99%, so on and so forth. And these are actually more accurate z's since they have 3 decimal places. The z table only has z values going out to the second decimal point. So this is more accurate so long as the confidence level is one of these 4 confidences. Now, if it's a confidence which is not listed here, like 93%, then we have to backtrack, go look at the z table, and try to figure out, well, what z would have that level of confidence. All right, so we can do that, but most of the time, the z value we're going to use is one of these on this table. Now, we also have here, this does a nice job of showing us, so long as we have a large enough sample, then my confidence interval with 1 minus alpha percent confidence is created by taking my sample average plus or minus the z, whatever that is for the confidence level we need, times the standard deviation, and we're on our way. We're able to create these confidence intervals. Okay? So this is the big punchline from section 7.2. But notice the keywords here, as we're requiring that these have to be large enough samples, right? We keep saying this, that for the central limit theorem to kick in, we need the sample to be large enough that we can trust that the standard deviation for my sample is equal to the population standard deviation. Okay? So even if the population standard deviation is unknown, then the sample standard deviation is assumed to be close enough because the sample is large enough to make this an accurate approximation. Okay? So that's just listed here in our requirements. First, we need a random sample in order to avoid bias. Secondly, we need a sample size to be large enough. What is large enough? We're finally ready to say a sample large enough needs a sample size greater than or equal to 30. So long as the sample size is greater than or equal to 30, then we can create these confidence intervals using z-scores and using the z-table to determine what z is going to create these different confidence intervals that is supposed to encompass 90%, 95%, whatever confidence level we want of the entire population. Okay? So we're going to do another example here. We have this airline example where they're trying to study what's going on with their revenue situation when they have empty seats on their planes. So I'm going to turn off the screen share as we work through this example. This is example 7.3 on page 321 of the textbook. All right. So in this example, unoccupied seats on a flight leads to a loss of revenue for the airline. So they want to try to avoid that. They want to make sure that their flights are as full as possible, so that they're not losing money on those empty seats. Okay. So they have this large airline where they're trying to estimate the average number of empty seats. If this average is too big, then okay, they got to do something to try to make that average smaller. If the smaller is already small, well then great, they don't have to worry about it. There's already not that many empty seats and they're not losing money. This is only an issue if the average is too high. Okay? So they're trying to estimate the number of unoccupied seats for a flight over the past year. So to do this, they look at records from 225 randomly selected flights. So we have 225 randomly selected flights. So this meets our requirements for, first of all, it's random, and the sample size is large enough. So great, we can use the z-score to create a confidence interval. Right? And the number of unoccupied seats is noted for each of the sampled flights. Now this data is collected, and it's displayed in a printout here in the notes, or here in the textbook, all right? So from the sample, they find they have an average, this is a sample average of 11.596 with a standard deviation of 4.103. Okay? And so now we want to know with 90% confidence, what is the interval that would include the true population average? Okay? So with 90% confidence, what is the population average? How many empty seats do they have on their flights on average? Okay. Well, it's the same formula as before. X bar plus or minus my Z alpha times the sample distribution standard deviation. Okay. So we go back to that table we were just looking at to try to figure out, well, what Z alpha should I be using? And from that table on page 320, I'll share my screen here again. When we want 90% confidence, alpha is 10%, alpha over 2 is 5%. The z we need here is 1.645. I'm going to copy that here on the board for us. 1.645 as our z alpha. Now I'll turn off the screen share again. So we have our z value, 1.645. All that's left is to create the interval. Okay? So we have 11.596 plus or minus 1.645 times the standard deviation divided by the square root of the sample size. And now this is our final calculation to get to our final answer. All right, so we look at the bottom number. We have here 11.596 minus 1.645 times, we got this fraction here, make sure that's in parentheses, times 4.103 divided by the square root of 225. And we get here for the lower bound an answer of 11.146. And an upper bound, if I switch that minus to a plus sign, we have 12.046. All right. And so the true population average is somewhere between 11 and 12 here. Now, of course, we can't have a fractional number of empty seats. That wouldn't make sense here, right? This is just an average. It's an approximation for the number of empty seats. But we do see, well, somewhere between 11 and 12 seats, or those are the two options, right? It could be 11 seats are empty, or it could be 12 seats are empty, somewhere in between there, okay? Or between those two options. Now then the airline has to decide, is that number okay, or is that number not okay? Is that too high, in which case, on average, are they losing too much money? Or is it okay if they have that many empty seats and it's not going to hurt the airline in the long run? That's a different kind of question where they have to look at their own finances to determine how much money are they actually losing on that, and is that enough lost money to actually be an issue? Or if it's a small enough amount of lost money, then maybe they're okay with this average, all right? But the first step was to determine how many empty seats do they have on average. Once they know that, now they can proceed to determine, is that actually a problem or not? Okay? So we have our final answer from this exercise at the end of section 7.2. And then lastly, we want to look at section 7.3 in this video. Okay, so what's 7.3 all about? Well, now the issue is, as we've just seen, the sample size has to be large enough, meaning the sample size needs to be greater than or equal to 30. But what if the sample size isn't large enough? You know, in some examples where this might happen, if maybe you're studying a rare disease that exists in the population, you're trying to determine different types of treatment plans and trying to figure out what treatments work or what treatments don't work. Because it's a rare disease, there might not be that many people out there to include in the sample, right? There might already be a small population to pull from to sample, right? In which case, despite our best efforts, we just can't create a large sample size. So what do? We can't use the z-score then because the central limit theorem falls apart. That theorem is only true when n is large enough. If it's not large enough, then we don't know if my sample data is actually a good approximation. We don't know if the sample standard deviation is actually approximately or close enough to the true population standard deviation. Okay, that's what the issue becomes here when we have a small sample size. So how do we fix this? Well, instead of using a t-score, we can use what is called a t-score. So what is a t-score? Well, first, let me draw this picture to try to explain what's going on here. So when we have the normal z distribution, we have, oops, not that. We have something that looks like this, where I've got this large kind of clustering in the middle, where I have this high frequency around what we think is the average, and this is the normal z distribution. And we're able to use this as an approximation for the true population because the sample size is large. I have enough data, but I have this piling up frequency in the middle to give me confidence that, yeah, wherever I see this clustering, that's probably where the true average is. But for a t distribution, I have a small sample size. Because the sample size is small enough, or smaller, I'm not able to get this large frequency clustered in the middle. I might still have some kind of hill shape around the average is supposed to be, but it's not going to be as extreme because the sample size is smaller. I can't reach a frequency that high with a smaller sample size. And so for a t distribution, it sometimes may look something like this instead. All right, so this is the normal t distribution, okay? And so unfortunately, it's just not as accurate as the z. And while we still have a hill shape, maybe in the same kind of area, but notice if I'm trying to capture some amount of probability, well, this hill shape for the t does not reach as high. So I'm not going to have that same like 47% or whatever here in the middle because I don't have as much area there in the middle. The height is lower. And so in order to get the same confidence, I oftentimes have to go farther out to the left and right. And so for t-scores, as opposed to z-scores, we may have to use larger and larger t's to go farther away from the middle in order to create the same level of confidence. Okay, but how do we actually calculate t? What is my formula for t? Well, this also depends on what is called the degrees of freedom. T's are found by first, well, what is your sample size? If your sample size is large or bigger, if it's close to 30 but not quite 30, then we have more degrees of freedom. We have more accuracy. But if my sample size is small, like 2 or 3 or 4 or something, then my degrees of freedom are also small. I have a less accurate picture of what's happening here. Okay? And so degrees of freedom, degrees of freedom. This is called DF in the textbook, abbreviated DF for degrees of freedom. And this always equals n minus 1, where n is the sample size. All right, so we need the degrees of freedom. And then second, we still need to know, well, what alpha am I talking about, right? How accurate do I want to be? So for example, if I have a sample size, if given a sample with n equal to, in this case, n is 5, find t alpha over 2 for a, let's see, this is with a 95% confidence. For a 95% confidence interval. All right, so this is what we're trying to do. If we have a sample with n equal to 5, so small sample size, I can't use z-scores. So instead, we're going to use t-scores, which t's are an approximation for z values. Okay? Now, we find this by, what is my t alpha? Well, the t alpha, just like z, depends on how much confidence do we want. If I'm looking for 95% confidence, then that means there's a 5% chance of error. So I have 0.025 to the right in that right tail. And I have 0.025 in the left tail. All right, so I'm trying to figure out what t value this is. How far to the left or right do we need to go? For that, we have a t table. Just like we had a z table, but now we're looking at a t table. And so we'll go to the textbook here. And the way to read this table is to first determine, okay, what's your degrees of freedom? For the example we're doing right now, the degrees of freedom are 5 minus 1, or in other words, 4. We have a degrees of freedom of 4. Once we know that, okay, looking across the top, we got to figure out, well, what's my t alpha? Now the picture here is only showing one tail. Don't let that kind of confuse you. The alpha here for our question was 5%, but in this picture, this is the alpha for one of the tails, okay? For our purposes, we know the right tail is supposed to be 0.025. So we're looking at the column where I have t subscript 0.025. That's the column I want in order to have 95% confidence. But here's where the degrees of freedom kick in. If I have more degrees of freedom, we have more accuracy, closer accuracy, and so I can use smaller t values. But if I have a small degree of freedom, I have less accuracy, then I have to use a larger t value to go far enough to the left and right to really capture enough of the population sample data there. Okay? But for our purposes, when we have degrees of freedom of 4, an alpha over 2 of 0.025, then we need a t alpha over 2 of 2.776. So it's highlighted here for us. Once you have your t, then we use it the exact same way as we would for z. When you're trying to create your confidence interval, we then use, well, whatever my sample average was, plus or minus t alpha instead of z, and that is multiplied by the standard deviation divided by the square root of n, which is our sampling distribution standard deviation, right? So it's the exact same formula we've been using, only we have to use t instead of z, and that t value is found by going and looking at the t table, right? And so that is the whole process for creating these confidence intervals, which first depends on how large is the sample size. If the sample size is large enough, if it's greater than 30, then we can use the z-scores, just like we did in section 7.2. If the sample is too small, then we have to use t-scores, but it's still the same formula where I'm just replacing z or t depending on the sample size and what we're using here. Okay? So this is section 7.3 and wraps up our examples here. All right. Now we don't have, unfortunately, I didn't have the time to publish a participation question for this video. So there is not a participation question associated with day 18, but we will have participation questions for the days after that. All right. So no worries about participation for this video. We just want to wrap our heads around section 7.2 and 7.3. And that will wrap up the material for this video. Okay. In the next video, we're going to look at sections 7.4 and 7.5 to finish up chapter 7. We'll talk about some special cases for creating confidence intervals, where what if instead of an average, what if I'm trying to estimate a proportion or a ratio? What does that look like? How do we go about that process? That we're going to talk about in the next section, okay? As well as talking about our sample size can be used to really control, well, how big is this plus or minus thing, right? I mean, if n is small, this might be a big piece on the right side, in which case my interval could be bigger. Well, if I want high accuracy, I would like my interval to be close together so that I can say, yeah, with more certainty, it's close to this number. But if it's like, for example, yeah, I think the average is 20 plus or minus 30, well, that's a big interval. That's like not really useful, right? So how do we control that? By making the sample size really large, we can control how big the window is for our confidence interval. All right, so we're going to see that in section 7.5 in the next video. Okay, so that's it for this video. If you have questions, feel free to email me. Feel free to come by office hours. Let me know if you're having any trouble or any issues. Otherwise, best of luck. I will see you all in the next video. Have a great day.